Alright, so we have another rule for trying to find derivatives, and this rule is going to focus on composite functions, which you'll be surprised at how often this rule can come up. This is called the chain rule. So, first thing to remember is that a composite function is obtained by plugging one function into another function. So, f of g of x is the same as f of g of x. So we call f of x the outside function. And throughout these notes, you might see me refer to it as the function O. And we call g of x the inside function. And throughout these notes, you might see me refer to it as I. So, the chain rule says the derivative of f of g of x is the same thing as f prime of g of x times g prime of x. In terms of these i's and o's, it's the derivative of the derivative of o with I plugged in for x times the derivative of I. So what we're saying in words is the derivative of the outside function with the inside function plugged in times the derivative of the inside function. Alright, so let's say we wanted to go ahead and find the derivative of this function x to the 6th plus 2, all in parentheses, to the 10th power. Now, one thing we could do is we could go ahead and expand this. But I don't know about you, but I don't really want to FOIL this entire thing out. That would be a lot of work. And so the hardest part about finding the chain rule is identifying what your outside and inside functions are. Now, your inside function is usually going to be the thing that you wish you could just take the derivative instead. It's the thing that you look at and say, well, I know how to take the derivative of that. In this case, the thing we know how to take the derivative of is x to the 6th plus 2. That's a pretty easy derivative. But if we take that and raise it to the 10th power, that might be hard to do. But what that means is that we're just taking this and raising it to the 10th power. So our inside function we know is x to the 6th plus 2. And our outside function here is going to be x to the 10th. Because essentially we're just saying, I want to take all this, raise it to the 10th power. And so that means that the derivative of the outside function is going to just be 10x to the 9th, and the derivative of the inside function is going to be 6x to the 5th plus 0. So 6x to the 5th. So then if we want to go ahead and find y prime, we're saying that it's the derivative of the outside with the inside plugged in for x times the derivative of the inside. And so here, if we're plugging in the inside into x, we have 10 times the quantity x to the 6th plus 2 to the 9th power times 6x to the 5th. And so we can rearrange this a little bit, and we get 60x to the 5th times x to the 6th plus 2 to the 9th power. Alright, the next thing we're going to try to do, we're going to have a lot of examples in this, and at the end there will be more examples for you to try on your own. So say we wanted to find the derivative of f of x equals sine cubed of x. So remember, we can think this as being sine of x to the 3rd power. And so here we know how to take the derivative of sine, or at least if we watched the last video we did. And we're basically taking it and raising it to the 3rd power. So the outside function is x cubed. We're taking a thing and raising it to a 3rd power. and the inside function is sine of x. So the derivative of the outside will be 3x squared, and the derivative of the inside will be cosine of x. So then f prime of x will be 3 sine of x squared times cosine of x, or just 3 sine squared of x times cosine of x. So again, how we did this is we said we're looking at the derivative of the outside, but instead of plugging in x, we're plugging in the inside function, so sine x replaces x, and then times the derivative of the inside function. All right, 2 examples down, a lot to go. So one common use of the chain rule is going to be the general power rule. We've kind of seen this already, and we'll see a few more examples. Say we've got some function being raised to the nth power. This is going to be the same as taking n times that function raised to the n minus 1 power times the derivative of that function. Essentially, we're saying that the outside function is x to the n, and the inside function is whatever g of x is. And so the derivative of the outside will just be n times x to the n minus 1, and the derivative of the inside function will just be the derivative of whatever the inside function is, g of x. So if we wanted to find the derivative here of f of x equals 4 over x minus 6, or 6 minus 2x to the power of 5, this is the same as 4 times 6 minus 2x to the power of negative 5. And so using this generalized power rule, if we know that the outside function is 4x to the negative 5th, and the inside function is 6 minus 2x, then our outside's derivative is going to be negative 20x to the negative 6th. So again, we bring the exponent down and we multiply by it, and we subtract 1. And the inside's derivative will just be negative 2. And so f prime of x will become negative 20 times 6 minus 2x to the negative 6th times negative 2. Or, in other words, it'll be 40 over 6 minus 2x to the 6th. If we wanted to find the derivative of h of x, when we have root 3, this is actually raising to the 1/3 power, but since it's in the denominator, we can rewrite this as being x squared plus x plus 1 raised to the negative 1/3. And so again, the outside function here is going to be x to the negative 1/3. The derivative of that will be negative 1/3 x to the negative 4/3. And so the inside function we see is x squared plus x plus 1. And its derivative will just be 2x plus 1. And so h prime of x will give us negative 1/3 times our inside function raised to the negative 4/3, so x squared plus x plus 1 raised to the negative 4/3, and then times 2x plus 1. There are probably some natural questions here about when is simple enough. This is simple enough. I think even WebAssign will find this to be simple enough. So if you're worried about these negative exponents and trying to rearrange things, don't worry so much about that. Alright, so now let's say we wanted to find the derivative of g of t, which is going to be cosine of pi times t squared. Here, we really know how to find the cosine of x, or cosine of t. When we plug something else in, that's where we have some difficulty. So our outside function here is actually going to be the cosine of t. and our inside function will be this pi t squared. The derivative of cosine is negative sine, and the derivative of pi t squared will be 2 pi t. And so in finding the derivative g prime of t, we will take negative sine, and then we'll replace the t with our inside function of pi t squared, and we'll multiply it by the derivative of the inside function, which is 2 pi t. And so we could even rewrite this to make it negative 2 pi t sine of pi t squared. Alright, so far we kind of just said, hey, here's the chain rule. Why does it, but never really said why it works. So if you're not interested in this, maybe skip a minute ahead. But if you are, great. So if we want to think about why the chain rule works, if we consider some big function f of x, which is comprised of a little f of x composed of g of x, the limit definition of this says we want to take the derivative by taking the limit as h approaches 0 of f of x plus h minus f of x over h, replacing that with what we've just called it. We're really taking this g of x plus h minus, or sorry, f of g of x plus h minus f of g of x over h. And so often what happens in mathematics when you're trying to prove things, this is not a hard and fast rule, but a lot of times you end up needing to create what's called a ghost term. So if you notice, this is something we can multiply by and is technically true because this is something over itself, which is 1. And so in rearranging this, you get g of x plus h minus g of x over h, which when you take the limit of this as h approaches 0, becomes g prime of x. Meanwhile, by putting the other part over here, you actually end up getting something where, since you have this and this matching up so nicely with this and this, you can replace g of x plus h with u. And so this comes to a rewriting of the definition for this derivative, which ends up giving you the derivative f with g of x plugged into it. So this is actually our definition of derivative at a point, which ends up helping us out. Alright, so let's keep going with a few more examples. Say 5 more examples. Let's say we wanted to find the derivative here of h of x, which is equal to x squared minus 1 times 2 cosine of x. So this is actually going to be a product rule and then a chain rule. So here, if we look at this, this is not something we're going to need to worry too much about, but cosine of 2x is going to be a problem for us. So if we do the product rule, our first function is x squared minus 1. Its derivative is 2x. And our second function is cosine of 2x. In order to find its derivative, we want to consider our outside function to be the cosine of x, and our inside function to be 2x. So the derivative of the inside is really easy, it's just 2. Derivative of the outside is also not too bad if you remember the rules. It's negative sine of x. So that tells us then that g prime of x is going to be negative sine of 2x times 2, or just negative 2 sine of 2x. So, with all this kind of ahead of time work done, product rule says that we want the first times the derivative of the second, so this will be for h prime of x, we want x squared minus 1 times negative 2 sine of 2x plus cosine of 2x times the derivative of this, which is just 2x. Now, you could go ahead and rearrange this if you'd like, but everything should be good to go there. In fact, the only thing you might want to do is, because there's a negative here, you might want to take and rewrite it as this minus this, but this is totally acceptable and good to go. Is this why he taught us trig derivatives? Because he wanted us to have more interesting examples with chain rule? Kinda, yeah. It's a perk. Let's say we want to find the derivative of y, which is equal to the square root of 1 plus cosine of x cubed. So this is 1 plus cosine of x cubed raised to the 1/2. So we've got a chain rule. So the outside function here is going to be x to the 1/2. So that's what we have here. And the derivative of the outside is pretty easy. It'll be 1/2 times x to the negative 1/2. The inside function is 1 plus cosine of x cubed. But if we want the derivative of that, doth my eyes deceive me? Is that going to be a chain rule inside of a chain rule? Oh, that's exciting. Okay, maybe you guys don't think it's exciting, but I think it's exciting. Alright, so here, our outside function, yes, we get a chain rule for our chain rule. It's getting off the chain in here. Is 1 plus cosine of x, and that inside function then will be x cubed. So essentially, we know how to take the cosine of a thing, we know how to take the derivative of 1, but we don't know how to take the derivative when we have something plugged into cosine. So that thing inside of cosine will be the inside part. And so I prime will be 3x squared, and the derivative of the outside, of course, derivative of 1 is 0, and so we get negative sine of x. So in order to find this derivative then, using that chain rule, we will have the derivative of the outside, or inside is something we'll multiply by at the end. We get negative 3x squared sine of x cubed. Okay, exciting stuff. We've got chain rules in our chain rules. So, we want the derivative of the outside with the inside plugged in times the derivative of the inside, which it was a little bit complicated to do. So that means in the end y prime is going to be equal to 1/2 times 1 plus cosine x cubed to the negative 1/2 multiplied by negative 3x squared sine of x cubed. All right, that was an exciting example. Let's see what other sorts of things we're going to play around with. Say we wanted to go ahead and find the derivative of sine of 1 plus x over 1 plus sine of x. Now, this is a quotient rule. We have one thing divided by another thing. And in using the quotient rule, we need to know both the derivative of the numerator and the denominator. So remember, it's low d high minus high d low all over low squared. But we don't know what the derivative of sine of x is, or sine of x plus 1 is. So the outside function here will be that sine of x, and the inside will be 1 plus x. So that tells us then that the derivative of the outside is cosine of x, and the derivative of the inside unfortunately is not all that interesting. It's just 1. So we want low d high minus high d low all over low squared for this. So y prime will be low, which is 1 plus sine of x, times the derivative of sine of 1 plus x, which is going to be cosine of 1 plus x times 1, but again, that's not too exciting, minus the numerator, sine of 1 plus x, over the derivative, or times the derivative of the denominator, which is just going to be derivative of 1 is 0, derivative of sine is cosine. So times cosine of x, all divided by 1 plus sine of x, quantity squared. So wait, we can have multiple rules going on at the same time? You betcha. Aren't these fun? I think they're fun. I hope you think they're fun too. I hope it's not just me playing around in my head thinking they're fun. Although it probably is. Alright, so let's say we wanted to find the derivative of this function, g of t, which is 2t plus 5 divided by 8t plus 7, whole thing raised to the 5th power. This is a chain rule where the outside function is equal to t to the 5th, and the inside function is going to be equal to 2t plus 5 over 8t plus 7. Derivative of the outside will be 5t to the 4th, which is not so bad. But in order to find I prime, we need the quotient rule. So in order to find this, it'll be low d high 8t plus 7 times the derivative of the numerator, which is 2, minus high d low, so 2t plus 5 times the derivative of the denominator, which is 8, all over 8t plus 7 squared. So then our g prime of t will be 5 times the inside function, 2t plus 5 over 8t plus 7 raised to the 4th power times the derivative of the inside, which is this lovely monstrosity. So that is 2 times 8t plus 7 minus 8 times 2t plus 5 all over 8t plus 7 squared. Now again, there's only so much really one could do to simplify things. So as long as you didn't make any minor mistakes in your process, all the way through all these side steps, you should be good to go. That part, though, is very tricky, so definitely take advantage of the discussion boards and my help when trying to figure out why you just can't figure out this very complicated derivative. And again, these are very complicated derivatives. Don't feel bad if you miss a minus sign somewhere or something. Alright, this is going to be the last example we talk about. This is going to be us trying to find the derivative of this function. So this is us trying to find y prime for sine of cosine of sine of x. Now this is the chain rule you never thought you'd have to dream about. So this is going to be a chain rule, and so we'll have our outside function be sine of x, and the inside function is the cosine of the sine of x. So the derivative of the outside will just be the cosine of x. Derivative of the inside will be another chain rule. And so here we have our outside function as cosine of x and our inside function as sine of x. So the derivative of that outside function is going to be negative sine of x and the derivative of that inside function will be cosine of x. So trying to find this I prime, this will be negative sine of x, sorry, not of x, of sine of x, times the cosine of x. Running out of room on the page. And so this again comes from taking negative sine and plugging in the inside function of sine of x, and then multiplying by that derivative of cosine of x. So, if we want to go ahead and complete this chain rule, we need to take the outside cosine of x with this plugged in and multiply by this derivative of the inside. So that means dy dx is going to be equal to the cosine of the cosine of sine of x multiplied by negative sine of sine of x times the cosine of x. So again, this is the inside. So it is equal to this giant monstrosity. And again, make sure you've got your parentheses right. Parentheses are another place where you can kind of very easily get things wrong when you're trying to go ahead and set things up in MyMathLab or WebAssign. So sine of x, cosine gets encapsulated, but you got to make sure you close off this cosine as well. So you need one more parenthesis there. And then sine of x, sine there, and I wanted to multiply by this whole thing, so I'll finish off those parentheses as well. See, even I make mistakes on parentheses, so don't feel bad if you are. Alright, now the remainder of what's on here, on this sheet, there are more examples of trying to find these derivatives. So there are 5 more examples of very complicated derivatives, and your goal is to attempt to find them. I will make sure to post this on Blackboard, and so what that means is you will be able to look at the scanned version of these, and the work will be shown, and you'll be able to kind of check your work. If you're trying to figure it out before you see the scanned version of these, feel free to post questions about them in the discussion boards. Talk about them, talk to each other. If you have any questions, as always, let me know.